Star Cloud 1, separation confirmed.
This is the first launch of a data center in space. And here, Elon and Jensen seriously discussing putting them on orbit. My first thought was, are you serious? Then it got far more interesting, because it's not just them. Google, Amazon, everyone is circling the same idea. There is something about space that keeps pulling us back.
The next step beyond Earth data centers is our Earth orbital data centers. And we'll be launching with SpaceX orbital data centers at the 100 to 200 gigawatt per year. What if you want to go beyond a mere terawatt per year? In order to do that, you have to go to the moon.
I've spent the last decade designing microchips that live or die by physics. That's why this episode is personal, because this idea sits right on the knife's edge, because it's either pure madness or inevitable next step. Subscribe to the channel and let me explain. We are building gigawatt data centers, and these are not just big buildings with servers. It's AI supercomputers the size of cities, millions of GPUs, and we built power plants next door just to keep them alive. And the most unglamorous part is cooling, because these campuses don't just consume electricity, they devour water, they drain rivers, just to stop silicon from cooking itself to death. But what's becoming even more scarce than power and water is time. That's why hyperscalers are in a land grab. Speed is the mode now. But on Earth, permits take years. Land is limited. Power grid is sold out. And the roadmap says we need 100 times more compute by 2030. If this trend continues, we don't just run out of power, we run out of Earth. So maybe it's time to put the cloud in the clouds. I know it sounds ridiculous, but space is tempting. There is no land limits, and in theory, unlimited solar power. It sounds clean and infinite, but this idea is insane on so many levels. That's why I can't wait to unpack it today. We will do it in 2 layers. Plan A, put data centers in orbit. Plan B, put data centers on the moon. So what would it actually take to build a tiny 20,000 GPU data center and make it fly over your head? Before we launch anything, we have to be honest about what an AI data center is. Because launching GPUs to space is easy. Launching a functioning AI data center is not. On Earth, a data center is surrounded by invisible infrastructure. Power comes from somewhere else. Cooling is an entire science. Fiber stitches thousands of servers into one giant AI supercomputer. In orbit, all of that disappears. So let's run the checklist. First, to launch a data center in orbit, you need compute. That's the easy part. We already know how to build absurdly powerful GPUs. But the moment you leave Earth, silicon enters a different battlefield. Space is brutal to chips. It's constantly bombarding them with high-energy particles. So we need chips that can survive this huge amount of radiation. You don't see these particles, but they flip bits in memory, corrupt calculations, slowly degrade transistors. Space slowly kills your servers, 1 bit flip at a time. On Earth, the atmosphere and magnetic field absorb most of that. In low Earth orbit, you still get partial protection, so it's survivable, but not forgiving. Which means you can't just throw a rack of GPUs into orbit. You have to shield them from all the sides carefully. We need physical shielding that blocks particles without adding too much mass. Technically, this is solvable, and we already have proof. Startup StarCloud already sent NVIDIA Hopper GPU into space. And it's already about 100 times more powerful than any computer previously operated in orbit. And it's already running inference in space. So the question is no longer, can GPUs survive up there? The question is, does it make any sense economically and technically? Because the moment you turn these GPUs on, they start pulling power. And power is the least insane part of that story. Because on Earth you have clouds, night, bad weather. In orbit you just get sunlight, and a lot of it. At first glance it looks perfect. You unfold solar arrays, face the sun, collect energy, run your systems, charge batteries for eclipse. Repeat every orbit. At small scale it works beautifully, until it is a data center. Because the moment you scale to real AI compute, everything changes. On Earth, modern AI campuses already sit in the gigawatt range. Of course, the first orbital proposals are more modest, tens of megawatts. StarCloud, for example, is aiming at roughly 40 megawatts. That's about 300 NVLink 72 racks with about 20,000 GPUs in total. Now, let's run the numbers. 10 square meters of solar panels gives you just a few kilowatts. Scale that to 40 megawatts and the geometry explodes. You're looking at something like a 350 by 350 meter solar array, over 100,000 square meters and roughly 400 tons. Just picture it, dozens of football fields of solar panels flying over your head at nearly 8 kilometers per second. That's massive, but not impossible if delivered in pieces. And the upside is real. In orbit, solar outperforms ground systems by at least 10 times. Imagine we shoot all of that to space and solve power. Finally, we've got an AI data center that we won't be able to plug off anymore. And just as instantly, every watt of power you generated turns into your new problem: heat. That's when the dream collides with physics. Which sounds ridiculous, right? Because space is cold. And that single idea misled more engineers than anything else. Because your GPU doesn't care about the temperature in space. It cares whether the heat can escape silicon. Everyone thinks that space is cold. That's why this problem is so dangerous. In low Earth orbit, you're essentially sitting in near-perfect vacuum. There is no air, no medium to carry heat away. And the higher you go, the more absolute the vacuum becomes. Space is cold, but vacuum is an insulator, which actually makes things much harder to cool in space. On Earth, heat disappears easily. Air molecules collide with hot surfaces and carry energy off. Water pulls heat away even faster. In space, none of that exists. You cannot dump heat into space. You can only radiate it away. And radiation is slow. Typically, it's hundreds of times less effective than convection or liquid cooling on Earth. That's why satellites carry radiators, huge panels whose only job is to dump waste heat into darkness. This is where the fantasy meets thermodynamics. Radiative cooling follows the Stefan-Boltzmann law. In plain terms, if you want to dump megawatts of heat without melting your hardware, you add surface area. A lot of it. For a 40 megawatt orbital data center, the math lands in the range of 120,000 square meters effective area. That's about 15 to 20 football fields of radiator wings in orbit. This means radiators must be huge compared to the relative compute load, and most likely implemented as two-sided panels. But here is the critical part. Radiator mass compounds the problem. It scales with how much heat you have to reject. If we are using a standard spacecraft estimates, you're looking at roughly 400 to 800 tons of radiator hardware for a 40 megawatt data center. And that's just for cooling. At the current launch prices, that's in the range of $2 to $4 billion just to launch the Radiators. And when launch cost will drop to something $500 per kilogram with Starship, you're looking at something like $200 million to $400 million just to launch the cooling. So yes, Starship helps, but even in the best case, we are looking at hundreds of millions of dollars just to launch cooling. And surprisingly, from here on, it's only getting worse and worse. Electronics in orbit don't sit at one temperature. In low Earth orbit, a spacecraft circles the planet every 90 minutes. One moment, it's in direct sunlight at 120 degrees. Minutes later, it drops into shadow at minus 170. That's a 300-degree temperature swing, and this thermal stress accumulates over its lifespan. Every orbit, all day, every day. So in space, you need a different approach. That's exactly what Starlink does. The electronics inside is wrapped into multi-layer insulation, thin reflective foils that block most solar radiation and trap internal heat. Small onboard heaters kick in during eclipse so batteries and processors don't freeze. The result is a controlled internal range, from 10 to 60 degrees inside, while outside, space is trying to tear it apart. It works at satellite scale, at few hundred watts. But now scale it to a megawatt data center, and that's a huge jump, with no proven solution. So suddenly, the cold vacuum of space becomes the hottest engineering problem. On paper, space data centers look elegant, but the image changes fast. It's not GPUs on the orbit, it's radiators and panels in orbit. But even if you solve heat, you still need to talk to Earth. Because if the results can't get down, the compute doesn't matter. It's just a very expensive space heater. Next, we will discuss the real killer of data centers in space and wrap up the economics and see if it makes sense to build a data center on the moon instead. But before we go there, I want to talk to you about my favorite tech magazine, IEEE Spectrum. It keeps me sharp on what's happening across the industry, including semiconductors, AI, robotics, energy, and space tech. When I want real depth and high-quality analysis, IEEE Spectrum is where I go. They consistently cover the trends that actually matter across the tech stack. Running a tech company and making a content in tech means I need signal, not noise. And that's exactly what I get there. I actually enjoy reading both digital and physical magazines. Digital gives you instant access, archives, and newsletters. Great for staying current. But the print edition is special. You sit down with a cup of coffee and really spend time with it, without distractions. I love to keep past issues on my desk and revisit them. That's my steady source of ideas. If you care about staying ahead in tech and engineering, subscribe to IEEE Spectrum now through the link below, and you will get an exclusive 10% off your subscription. If you enjoy my content, you will most certainly love their content too. And to me, that means a lot that they are sponsoring this episode. Now back to the space dream. And now things will get uncomfortable. Because on Earth, data centers are stitched together with fiber. Inside modern AI clusters, links are already pushing towards 1.6 terabits per second. That's the baseline these systems expect. Constant, high-throughput communication between racks, clusters, and users. So the moment you put a supercomputer on orbit, a question arises. How do you move that much data back to Earth? In theory, you can send enormous amounts of data through space using lasers. This is called free space orbital communication. You fire extremely precise laser beams between satellites, and those beams carry data at hundreds of gigabits per second. Starlink already uses it between satellites. Inside space, bandwidth can be actually incredible. We are talking about hundreds of gigabits per second. Because there is no atmosphere, no cables, just light. The real bottleneck is getting that data back to Earth, because the moment this signal hits the atmosphere, everything changes. Clouds scatter light, weather interferes, even turbulence in the air distorts the beam. You can work around some of that with phase arrays. These are flat antennas that steer and focus the signal into a very tight beam, so tight that enough of it reaches Earth. It helps, but it's still nowhere near fiber-level capacity. So here you end up with a strange mismatch. Massive compute in orbit and very narrow pipelines down to Earth. And the thing is, the further from Earth you go, the worse it gets. And I will come back to that in a moment when talking about the Moon. By now, the pattern is clear. Power is solvable. Cooling is brutal. Bandwidth is the weak spot. And even if you solve all of that, eventually something will break, because GPUs fail. Components age, and in about 4 years they are obsolete anyway. So imagine you want to replace a failed unit or upgrade the cluster. How do you go about maintenance? On Earth, we walk in, replace the rack, swap a part, and move on. In orbit, that's impossible. So the whole thing is designed for survival or for replacement. Both hurt. The moment you put a data center in space, physical maintenance disappears. No technicians, no quick fixes. Everything has to keep running on its own. So here the philosophy changes completely. You don't fix things in orbit. You just outnumber the failure. And this forces you to launch more capacity than you actually need. Extra nodes sitting idle, ready to take over the second something glitches. If one server dies, the system reroutes around it, the fleet slowly refreshing itself over time. Here, software becomes the first line of maintenance. Most of the things are fixed remotely. And from the outside, it looks like nothing happened. Only when hardware truly fails, you accept the loss. And then you wait for the next launch window and send up a replacement. This is how Starlink already works. They don't repair units, they replace them. New units go up constantly. Old or failed ones deorbit and burn up in the atmosphere. Right now it's happening at a steady cadence of 2 satellites a day. Satellites coming down, new ones going up. Most of the debris vaporizes before it reaches the ground. The problem here, it doesn't just disappear. What's left becomes a thin layer of particles high in the atmosphere. Aluminum oxides and other remnants that can linger for years. Scientists are still studying what that means for ozone and climate. Well, at small satellite scale, this model works. At data center scale, it's brutal. Moreover, every upgrade is tied to a rocket. And suddenly, economics start to dominate the conversation, because redundancy means extra hardware. Extra hardware means extra launches. And remember, tons of solar and radiators. And all of that becomes very expensive. And this is where the romance ends and the spreadsheet begins. Because if it's not cheaper or strategically necessary, it won't scale. Let's go back to our 40 megawatts orbital data center. That's about 400 tons of compute, plus 400 tons of radiators, plus 400 tons of solar. So more than 1,000 tons total mass. At today's launch prices, about $5,000 per kilogram, you are looking at least $5 billion just to lift a system like this into orbit. And that's only to get the mass of the planet. It doesn't include solar panel costs, compute cost, batteries, it doesn't include the cooling. And if you add all of this infrastructure, the costs are just exploding. We're coming to the kind of numbers that make even the richest hyperscalers pause. In the end, it all comes down to one simple matrix: watts per dollar. And at the moment, I'm not convinced the math here works. And I know at the moment this idea might already look like madness to you. Well, at some point it might start making sense, because launch costs are falling so fast. Companies like SpaceX and Stoke are pushing that curve down. Internal launch costs for SpaceX are likely far lower, at least 5 times, than public pricing. That's the only reason why anyone serious is even talking about orbital data centers. And it's also why Elon keeps bringing it up. But I feel like we're still missing a breakthrough or two to get there. But at the same time, the orbit is getting really crowded. There are already thousands of satellites up there. Put something the size of a floating data center into low orbit, and congestion becomes real. If you need to scale it to 1 terawatt, you need to go to the moon. Well, data centers on the moon. That's a real moonshot. Why to build a data center on the moon at all? Because Earth has limits. Power, land, permits, politics. The moon has none of those. Vast surface area. In theory, unlimited expansion. That's the attraction. But guess what? The further you go from Earth, the harder everything gets. And when you try to put a data center on the moon, our checklists get brutal. Let's run it. First, compute. Radiation on the moon is far harsher than in low Earth orbit. There is no magnetic field, no atmosphere, nothing between your hardware and space. Cosmic rays hit constantly, but solar storms is the real nightmare. A solar storm is a massive cloud of charged particles that can last for hours, sometimes days. On the moon, it hits directly. No protection. That means a steady bombardment of high-energy particles slamming into silicon, flipping bits, corrupting memory, triggering logic errors. A normal GPU would not survive long. A couple of days, maybe a week. So we need the radiation-hardened chips. But that explodes complexity and the chip size. Then we need to add heavy shielding around the hardware, and typically use a specialized chip process like silicon on insulator. Basically, instead of building transistors directly on silicon, you isolate them on a thin insulating layer. That separation reduces the chances that a particle strike triggers a cascade of current through the chip. It makes circuits far more tolerant to radiation. And yes, all of that works, but it's expensive. Radiation-hardened chips can cost 10 to 100 times more than normal chips, and they're usually slower. You don't want to put cutting-edge 2-nanometer GPU on the moon. The newest nodes are the most fragile. Transistors are so small now that a single high-energy particle can do more than flip a bit. It can knock out an entire computing core. With every transistor shrink, with smaller and smaller nodes, performance goes up, resilience goes down. Also, some suggest that you can just skip all this heavy protection, and of course you could, but then you bet that your multi-billion-dollar lunar supercluster will survive more than a month. Probably it won't. So you fall back to more mature nodes, like 7 nanometer. AMD has already some radiation-hardened designs, like SoCs and FPGAs, but so far no radiation-hardened GPUs. These are reliable, but not the cutting edge, which means you are already trading the performance for survival. And as if it wasn't enough, the moon adds one more complication. Dust. Fine, abrasive, electrostatic dust that clings to everything. It coats radiators, degrades optics, interferes with moving parts, slowly killing hardware over time. And that's before you've even turned the system on, because in the end, compute isn't the hardest problem. Power is. At first glance, this sounds easy. Solar energy is abundant on the moon. There is no atmosphere, no clouds, just pure sunlight. Perfect, right? Not quite. The moon rotates slowly. One lunar day lasts about 29 Earth days. That means roughly 14 days of continuous sunlight, followed by 14 days of complete darkness. During the darkness, solar output drops to zero. So now you need either massive battery storage or nuclear reactors deployed on the lunar surface. Both add mass. Mass adds launch cost. And once again, launch cost dominates everything. let's assume somehow you solved power and can survive 2-week night. Now you finally have a lunar data center. And now comes the question that ruins the mood. How do you cool it? Because on the moon, heat has no place to go. No air, no wind, no atmosphere to carry it away. But now at the moon, extreme temperature swings. Surface temperatures can swing from over 120 degrees Celsius in sunlight to below minus 130 degrees Celsius at night. In shadowed craters, it drops even lower. Your hardware isn't just hot, it's expanding and contracting constantly. Just like in orbit, radiators become critical. They have to be enormous, disproportionately large compared to the compute they're cooling. I'm sure at this point many of you are ready to give up on this crazy idea. But we haven't covered the worst part yet. Because the biggest killer isn't the heat, it's physics. Specifically, the speed of light. The moon sits nearly 400,000 kilometers away, which means every bit of data has to cross that distance. The only realistic way to move large volumes here is through laser optical communication. High-power infrared beams aimed directly at optical ground stations on Earth. In theory, this works beautifully. Laser links can reach gigabits level speed, which is enough for bulky data transfer. But light is only so fast. It takes about 1.3 seconds to travel one way from the moon to Earth. Even under perfect conditions, you're looking at roughly 2.6 seconds of round-trip latency. That severely limits the list of applications. So it won't work for real-time applications like AI inference, for what we use terrestrial data centers for. But it might work for data storage. Or large jobs where you process everything up there and then send the results down afterwards. Compared with low Earth orbit, where latency sits around 10 to 50 milliseconds, the moon feels distant. So what would make sense up there? Probably storage. But then you can ask an obvious question. Isn't storage already way too expensive on Earth? And yet, this is exactly what Lone Star Data Holding is experimenting with. Off-planet data storage. This is a strategy to keep the most valuable, important data off Earth. So if something goes wrong here, this is a way to back us up. Lone Star planned to build up tiny lunar data centers. They launched a test mission in March 2025, so last year, with 1 kilogram of compute plus SSD storage. But unfortunately, the landing didn't succeed. Still, the direction is clear. The long game isn't streaming or real-time compute. It's backup. If something catastrophic happens on Earth, the data survives somewhere else. Cold storage. And yes, extremely expensive one. So if you're not yet convinced that this whole idea is a little lunatic, let's talk about the final killer: economics. Getting mass to orbit is expensive. Landing payloads on the moon can cost 20 times more per kilogram than low Earth orbit. Everything must land softly, which is not guaranteed. So a small lunar data center quickly becomes a mega expensive project. Basically, you have to solve everything we've discussed for orbit and then add even more. Maintenance robots, replacement hardware, and autonomous repair. It's extremely hard to run a lunar data center entirely from Earth. At some point, you need local capability. Mining, possibly silicon, because the moon has plenty of it. And then manufacturing. A data center won't be enough. You need economy. That's why, for me, the only possible reason to build a data center on the moon is to build the economy on the moon. Otherwise, every problem that's already hard and expensive to solve on Earth is becoming even harder and more expensive to solve up there. So, are space data centers madness or inevitability? If we take orbit, the physics says it's possible. Economics says not yet. The moon, at the moment, feels a little bit out of the orbit. Even with all the free land, all the sunlight, all the theoretical scale, is any of this worth the effort? Still, there is something about space we can't stay away from. And I personally think we are still missing a couple of breakthroughs in energy and the way we compute before we can make such an endeavor. Subscribe to the channel not to miss them. Now watch this episode on the world's largest AI data center, or this one where I take you inside the secret chip factory to show you the smallest microchips to date. And I will see you there. Ciao!